Panel discussion. Okay, so all the invited speakers or their colleague, please come up and sit here. We are, yeah, please. Okay, please. Right? All right. So yes, I think for those who attended the past APNet know that this is the APNet panel discussion is a bit special. Matt, please. KK, Harry, please. Right. And our special thing is to we have academia inside. We have industrial spotlights, right? And so, all right. And the panel is designed in the way that I will start with, come with a starting question. Okay, this is just a leading question, and then follow that. So audience will be very interactive with panel members. They have some like interesting or radical viewpoints during their talk, right? And you may stand up and ask someone that some questions you have no time to ask during the talk or anything. It's not restricted to this as a topic, the things I wrote on the screen, okay? And for example, just now, someone asked Gil. Gil, by the way, sit here. He will be also talking if you have questions for him. And someone asked Gil, what is the boundary of scale out and scale up? Now, I think it is quite an amazing question that's still I don't know answer at all, okay? And also yesterday, like Professor Chen said FC is coming, right? CC is declining, right? That's also a radical viewpoint. If you agree or don't disagree, you can ask. All right. So I come up this topic. I think this we're networking like a workshop or conference, right? So we still care most about the networking research, and of course nowadays in the era of AI and LLM. If you remember, starting from 2023, when we come back to on-site conference, we start to talk about AI and network. And I would like to continue, right? That's the main thing these years and the many years to come, I believe. So a lot of questions, right? Scale up, scale out. What's the boundary? What's the definition, right? What's the metric? And we have Ethernet InfiniBand, right? Many 20 years or even more, we talk about this. Right? A lot of like consortiums, Ultra Ethernet Consortium, right? And also like UA Link, NV Link, right? Broadcom recently as scale up Ethernet, right? Huawei last night in the banquet said that Huawei will reopen unified bus, right? Quite amazing. And a lot of techniques, right? Recently we deal with AI training workload, right? Large flow, low entropy. We do packet spray, right? NVIDIA also, promote their adaptive routing, right? And real optimized, many terms, right? Many techniques, many definitions, many concepts, right? A lot of like consortiums, right? So very hot, extremely hot, but very chaotic, right? I think it's a lot of things unknown, very unclear. So my starting question is that, we have so many things. They are not exactly at the same layer, but I just list them, right? I come up with these slides, this new after during the launch. I also discussed with my students, right? It's very hard to have a very clear, I think, classification or clarify them. Okay, so my question for the panel members and Gail in the audience, and also what is, so many things here, what is clear, what is unclear, what is the trend, industrial trend, I think, and most importantly, what can we do? We have most of the audience are students, professors, right, researchers. A lot of things, at least, like this scale-up network, even to me, it's very largely, I know very little about that. I'm really eager to know more about this. So maybe let's start with this. I know we have, I discussed with Quinn, and I also listened to the talk of Gil. Maybe we can start from the Quinn, you want to share something, and then I also want to have Gil's viewpoint.
So for the scale up, scale out, I mean, it's actually, I see it's a history word. So let's look back. What is a scale out network? When I talk about the scale out network, we have a context. It's about the building the network for data center. Before we really want a big data center, what we do is what is comes with is a star topology. You know that we have a switch, a top of rack switch, and top of rack switch that's wire into some spine switch and got that. So it's not scale. So when we want a larger data center, actually we change the topology, make a closed network. Of course, I have other proposals, but finally we converge to the closed network to make it a scale. So let's come out the scale out issue. So why come back to scale up? Because you consider what is the bandwidth we have for our data center network. One I was working on data center back to 2010 something. We're talking about 10 gig, talking about 40 gig. And I still remember we have a proposal to the Azure network. So, why not upgrade to 100 gig? Then we got rejected because what's the use for? We have 40 gig level there, and there's no use. The utilization of the network is very, very low. It's about 10% or something, yeah. But something changed later. It's because of the AI. And we would need to train large models, so it takes a lot of bandwidth. We found that definitely 10 gig is not good. 40 gig is not enough. Even 100 gig is not enough. So we have the building this high bandwidth network. I mean, InfiniBand is one. NVLink is that. And how we start UB and Huawei is also to build this very high bandwidth. So this is what we call scale up. It's compared to the state of art. Not state of art, I mean, it is the state of the common settings. So it's like order of magnitude higher. So we call it a scale up network. But we look back I say, maybe it's not that clear cut of what is determined. What is definition about the scale up? How fast is a scale up? It's not very clear now, but back to a few years, we know it's clearly. We need some bandwidth that is more than like 40 gig, or even 8 gig or 10 gig, or 1 T gigabit to serve our models. But now we may need more. So I think that's definitely is a term, is the bandwidth that determine of the scale up. But something there's another concept I haven't been mentioned. It's also related to scale up. We call it tightly coupled or loosely coupled systems. Okay, so this is not particularly a scale up, but normally we believe that the scale up network, we can build tightly coupled system with a high bandwidth, low latency fabric. That means we could have this memory access. I think Gil makes a point that we have memory sharing memory, make it very make sense in this high-speed network. So, we still can share memory, in APNet, right? We have this RDMA, you can do this single-sided read-write, kind of memory semantic. But if its network is not fast enough, it doesn't bring too much attraction to the application developers. So if we have a very fast network and no latency, we can make this RDMA semantic or the memory semantic very attractive for the applications, for the model training. Also, we can also not only do read-write, we can do load and store directly from a processor to a memory location. So actually it's not memory-to-memory copy, it's memory to cache, memory to registers. So with that, we can do a lot of optimizations for the system to running that models really fast. So I think that determines what is scale up now is really high bandwidth. And with that, no latency, of course. And with that, we can build tight systems, tightly coupled systems. So let's define how this scale up network, I think.
Right. Yeah, actually, right before the session, I asked Kun about this question. I got part of his answers. Gail, do you have something to say?
So I just second, what you just said. Again, it's bandwidth and speed and everything, but I think an important part is the programming model. Scale up is usually load store. You just build one. For me, it's a GPU, right? No matter how many dies you have, no matter how many packages, I don't care about those. Those are just physical packaging. It's one GPU, load store, programming model. You have as many SMs or as many execution engines as you wish, but it's one compute engine, load store. By the way, we do see an interesting thing, if you look at NVIDIA GPUs, right? You have load store for scale up, you have send receive, but you also have put get on scale out network. But now we are going to see asynchronous load store, which is something that, it's an artifact of trying to scale up more efficiently, trying to do asynchronous load store. It's in between. It's not put get, but it's not a standard load. It's not a blocking load store because then you have too high latency at some point. It will be very interesting to see where this goes.
All right. So they have shared their viewpoint. You just keep it. We have this. I think, right. It's not surprised they may share some common viewpoint. Also have some different viewpoint because, as public, we know that Huawei has a scale up, maybe a class with 384 GPUs, right? And NVIDIA, their product, as far as know, NVL 72 GPUs, maybe. Okay, it's quite natural that they may have some different understanding about the architecture, the network. Okay, so I think there's a warm-up question. So starting from them, and I want to hear the other panel members have yes.
I want to ask a very high-level question to the industry members. I think we are all feeling that the era is shifting, right? So in the internet era, in the wireless communication era, the mobile computing era, the networking researchers were like core enablers. Right? The data communication, all this was core enablers in those eras. And after all, the hard research was done and industrialized, we keep trying to find, killer applications, right? Oh, we want to build this very high performance network. Where's the killer application? Now, so all of a sudden, AI is the killer application, right? So what's the role of networking in this new era? Do you feel like, as industry members, NVIDIA, Microsoft, do you feel that networking is becoming more important in this era? And what has changed, right, for the past 3 to 5 years?
Or is it the other way?
Huh? Yeah, is
networking becoming less?
Yeah, are we becoming more marginalized in this era of AI, or are we becoming more important? Yeah. Microsoft?
So actually, I'm working on system community. We actually asking the similar question: are we going to be, obsolete and stay irrelevant in the very near future, given the landscape of future intelligence? So I think that, but if you are looking at the network community, I think the problem is multifold, as very similar to OS, right? So system community evolved because of the killer apps, and so does networking community. So networking community driven by web traffic, right? That's the internet area, and for data center, data center networking is driven by data center workload, and for the AI, actually the interconnect. I'm not saying traditional networking, but the interconnect become much more important, right? In the foreseeable future, will become still very relevant. So I think that every community need to evolve and embrace new change. For system community, we actually embrace MLSys. So right now, I still remember like 2018 when I attend the OSDI, very few people talking about AI. They're talking about machine learning, right? So this year I attend the OSDI at Boston. Almost everyone talking about large language model. So that's a very clear change. So I think that whether you will be obsolete or stay relevant, it all depends on you, and whether we can figure out a way to stay, play some role at the main thing of the current era. And it's very clear the current era is the era of AI. So let's find some way, find some work to work for AI workload. That's my understanding. Thank you.
Yeah, I think those who ask a great question, and I just have some follow-up that want to kind of share. So first of all, I don't think I know much about scale-up and stuff, and this is obviously mostly driven by AI. And one thing I want to say is that if I look at what I like 20 years or 20-something years ago when I learned computer networking, and when I look at the way that I am teaching computer networking now, interconnect, as Fan was saying, interconnect was never part of traditional computer networking, in that realm. But right now, even without scale up, this hype, even without that, things like a meeting and other stuff is already making interconnect and other related things like networking. If we want to, if the networking community want to stay more relevant to the current development. So I feel like I now have to not just learn traditional networking, but then I have to learn things like computer architecture, PCIe switch, NVLink, that are things that are you've never seen in conventional computer networks textbook. So I think that's a great opportunity, obviously. But then at least for me personally, for things like for technical topics like scale up, then I think I still have to learn a lot before I would be able to comment anything like meaningful. But yeah, it seems like very exciting area yeah.
I have a counter to that. I studied my master's in '76. My first exposure to networking was reading one paper, going to the library. It was an assignment that I had for my class, which was to look at networking on a chip. And the more things change, the more things stay the same. My first task in digital equipment was to look at having a common interconnect for systems, networks, storage. These are all goes round and round. It's just that we're seeing larger scale, applications are a little different, but the more things change, the more things stay the same.
Right, maybe Alibaba, you have some experience to share just about this question.
Yeah, so I'm probably the least known person on the stage, but I sit in the front because there's no seat left. I first introduce myself. I'm Song Yang from Alibaba Cloud networking team. And so my perspective may from the cloud provider. And so talk about the networking part. I think as long as the compute unit is not big enough to do the job, and it cannot totally integrate with the memory, and there is always need for the network. And maybe the network is not the traditional concept of the network, because we always say like within the host, it's probably not the network but the bus. But I think the boundary between host network and within host network is blurred. And so I think the more computation we need and the more network we will need. So that would be a very prosperous area to learn and to stay.
Yeah. So next, I want to give opportunity to audience. You student here, you are free to.
Let me add one point.
Yeah.
So actually, the question I actually pounding a lot on Dongsu's question. So the short answer is yes, definitely. Connections, networking is really important for the AI. Why we struggle or not, because of say communication is not fast enough. But the things why Dongsu you ask this question. So I think it's kind of remind me a few maybe 10 years before when we start the cloud network research. The things that why the academic is basically, I feel the academic fund is isolated from this, right? Because this is just a game for big companies doing in cloud networking, I think, when we started. Yeah, it is, but later I found, so they're similar to the AI things. So not this is important, but not everyone in academic can do things on that and do machine. I think in the same situation when we consider like 2010, right, something like this. But things changed when networking community can work on the cloud network, because where the cloud company actually open models, data, and the tools that the community can work on something that makes sense, right? So I think that's maybe the critical part for this year, for the coming years, that maybe I think the model players, this infrastructure, the AI infrastructure, we should realize some tools, models, and the data that could have involved academic research on that. I think that will be this collaboration and the interaction may boost new innovations in this area. So that's definitely an important area, I think. Yeah.
Okay. Yeah. Audience, please, if you have questions, come up and can name the panel members to answer your for your questions. Yeah. Yes. Come up. Yes. Right.
No, there's no mic there. All the mics are here.
Okay, thanks for the opportunity. And actually, I want to discuss one question with you about congestion control. And from yesterday's talk, Professor Tian Chen has presented the idea that the flow control will be more and more important in the AI network in the future. And I just saw from your slide and put the congestion control right behind, closely to the load balance world. So I think maybe using congestion control is also very important. I also heard many debates on whether congestion control is necessary in AI network. So I want to know your opinion on this, maybe, or maybe you can share some real cases in practice. Thank you.
Okay, a short answer is yes, congestion control is extremely important. You know, scale is going up. We build very large networks, connect a huge number of GPUs. Mm-hmm. Traffic patterns are getting more and more complicated, right? You know, reduce, scatter, all gather. If you can do ring, you don't need congestion control. You can avoid congestion at first. But MOEs with sparse all-to-all, mm-hmm. And we see that, you know, not just in inference, also in training, we see that sparse all-to-all is becoming a very large part of the network workload. Definitely congestion is a problem. And building large-scale networks and avoiding congestion is almost impossible. Congestion control is an important part of enabling efficient utilization of the network. It doesn't live alone, right? It needs to be, a part of a package. The way you load balance, you will see more and more systems where GPU have more than one port, more than one network adapter. So you need to start with load balancing at the source, and then you have closed topologies with multipathing. So you need to be able to utilize the redundancy in the network, and on top of that, you must have congestion control.
So even with adaptive routing technology enabled?
Yes, with sparse, sparse all-to-all V can really cause many-to-one congestion, fan-in kind of, the standard, the good old congestion, right, of having multiple sources sending tokens to the same expert. They're asynchronous, it's kind of random sparsity, and you cannot really control that. So yes, many-to-one will happen in MOEs. MOEs is becoming a large part of the workload in training mostly. Also, it's also an issue with inference, but training, very large batches, many tokens, yes, congestion control is very important.
Okay, thank you.
So, Professor Tian, how do you respond to this?
Let me answer first. Okay.
No, okay.
At one level, these two, whether it's congestion or flow control, they're all doing the same thing, which is matching demand, instantaneous or otherwise, to available capacity. And depends on topology, depends on workload. The power is out everywhere. This is not me.
Push this. Keep going, green on.
Yes. So I don't see a big distinction between these two. It's where you manage the load, whether it is hop by hop, end to end, depends on the topology, depends on the workload.
Okay. So my response is that I think the congestion management, we need to distinguish the concept. Congestion management is definitely critical. We cannot avoid it. It's more and more important. So what I'm talking about yesterday is actually there are two concepts in congestion management. One is congestion control, is for the long term, like the you still need to select a route to do load balance, or whether your packet will sent out at this moment. This is congestion control. And what I'm talking about is flow control should be more and more important, because my intuition that in the for the technical part, our research has not paid enough attention to the flow control part. I'm not the one, only one to notice this, because I heard some rumor in the last year, in the end of last year, some of the big companies, they are training their AI clusters. They actually turn off all the congestion control protocols, only rely on PFC. I mean, the current, not the new technology Gil just gave us, it's not the new technology, just the old technology. They turn off the DCTQC and turn off all congestion control. They just use the PFC. And they are not researchers, but their results shows better results of the training, faster training. So that means something's wrong. Something's wrong with our current congestion control research, or their interplay between the congestion control and the flow control. So that's my point. I still agree with Gil that congestion management is very, very critical. The only my point is that we shouldn't pay more attention to flow control part. I mean, that's my point. Yeah, I need to clarify.
Okay.
Actually, I'd like to clarify a little bit on the congestion control and the flow control. I mean, so from the networking point of view, the older generation of principle is that such kind of mechanism should be more generic to any kind of workload, right? So as Jill mentioned that now there are irregular traffic patterns in AI workloads, like MOE, the sparsity and something. On the other hand, actually we have seen very regular traffic pattern on other part of the, like FFN, like the attention, right? Those kind of data movement is highly regular. So in my opinion, they open a new possibility to redefine or restudy, revisit the principle, whether your flow control, whatever it is, or congestion control, should be model specific. I think that's subject to the research of network community. Thank you.
Thank you. Before the next question, I have a quick question for the industrial, Gil and Kun. So, yeah, basically, actually, because we just talk about this flow control, congestion control, we also talk about workload, right? MOE, O2 or V, right? That's depend on workload. And another thing is, recently, in the past few years, have some topology for clusters. Google has TPUv4, right? Huawei has UB mesh, which take locality or some like spatial patterns, right, into consideration when design their interconnect. That's something I worry about a lot. Recently, Broadcom has 100T switch with 500 ports and 200 gigabit per second, like 500, 200G, right? And so for you, my question is, do you think the classical two-layer cloud network, span leaf, versus this UB mesh, TPUv4, which one you prefer? I need a very quick answer. Which one? Gil, please.
I don't think I have much to contribute here. No quick answer.
No quick answer, but okay. So, but what's your preference, right?
I don't even think I have a preference. You know what we're building? We build usually rail-optimized class, two-layer factory.
All right. All right.
Is it the only solution? Definitely not. Which one will be better in 2 years from today? I really don't know.
Okay. I get your answer. Kun, what do you think? Right.
I think my quick answer doesn't matter. They pick up a topology, they have their own choice. I mean, their own reasons. Okay, so, you know, for example, we have, even for DeepSeek, they have their engineering network with multiple rail without the top rack. So they just work for their traffic. So I think with more, when you know, models, when training models is really critical, it's a large enough workload, and it may be reason maybe some of these things is not reasonable, but I think there's a good reason to design special topology for a particular workload if the company believes that it is really important.
Okay.
Okay, thanks. I wanted to ask a question about the possibility of building an open ecosystem for the scale-up network. And compared to scale-up ecosystem is that like NVLink, UALink, they are quite closed. And we can just, we can only buy a well-built, tightly integrated system, and we can just use it. And I can't do any like the programmable parts on top of it. For example, if I want to do the virtualization, like I want to do programmable congestion control, and I want to configure it by myself, I can't do this. For the scale-out system, I have the devices like SmartNICs, DPU, and programmable switches. In the scale-up system, we don't have this. So is there any hope that we can change this in the future? And is there any efforts in the industry about this? Yeah, thank you.
Well, this is very high-level question. Right, he's my student. I didn't expect you to ask this high-level questions.
You underestimate.
Yeah. But anyway, good thing. He think a lot. Yeah. So who you want? This is. So.
Well, let me think. It's a really a good question. I think this, actually what you are thinking is about the decoupling. It's a decoupling. And also it's open, if the open protocols and proprietary protocols. I think that's the real questions you're going to ask, right? So I think there's, I still say there's still reasons for be open protocols and decouple and also tightly coupled and the proprietary the things. I think that, for example, if you go to some proprietary protocols, basically this reason is performance, okay, and also sure, yes, that put apart this business reasons be apart for the performance, and tightly coupled system also has a performance benefit. Yeah, it's true at the very early when the workload is very critical, you just need extreme performance. So I think they go to very tight system design. It's a reason, right? And then later on, maybe we always have these things like especially when Moore's law still effective. Then later on, if I say there is a high performance things, 2 years later now become commodity. You can get it everywhere. Even very small devices, very cheap devices, and then decoupling design become a popular. Yeah, and then you can really do a flexible things, what you want to do. It is good enough for you to put up this complete off-the-shelf things and to achieve your target. I think that's just things goes on. Yeah.
I see it as nature of the problem, right? Better understood, you want speed, you start doing consolidation. If you want lower cost, you do consolidation. We look at what happens on the other side. You want more flexibility, you disaggregate. And we are seeing this simultaneously in two different fields in networking. All you guys doing AI are looking like he's sticking the optics way into the processor. We used to say, well, we want to have everything nicely layered, disaggregated. You look at what is happening in the cellular world, they're saying every component needs to be disaggregated. So it's the nature of the problem, where you want flexibility, where you want performance and cost.
I think that's also the fun of the system research. Found the best trade-off in your situation.
Yeah, thank you. Also, I wanted to discuss a little more.
I have another answer. The extreme case of scale-up would be the wafer scale integration, right? Yeah. So in my view, the scale-out is like free trading, right? you have your competitive advantage, right? Everybody can, take something out of it, but in the scale-up version, the extreme version, it's like I'm only going to dominate, right, this industry. So there's a lot of hegemony and, fight against this dominating person, right? So I think naturally scale out would work better, since now, I mean, free trade was working really good, so, right? So but I think it will scale out, having everyone, respecting everyone, that's where actually the innovation comes from. One person dominating, I think, in some cases it would work, but in the long run, yeah, I don't think it's sustainable.
Right. Okay. So we have just like
Okay.
a few minutes.
I can switch to the other.
We can just offer one more question. Okay. Yes. One more question.
Hi, I'm Chen Yu from ByteDance. So, as a networking researcher, I work on a high-speed networking. We support like internal seed model training team. So one thing that I heard questions from the AI people, they develop models. Networking are like a black box to them. They don't know much about, say, congestion control or flow control, those type of stuff. And I think it's, in the era of AI, and specifically, it's very important for these applications to actually adapt to like the networking. It's important to like co-design these things together. I think actually DeepSeek is doing a very great job by saying this deep EP stuff. So my question is, what advice would you give for AI people when they are, like, say, designing the next era of the LLM model? So say, what type of the networking pattern is the most favorable for networking people? How would you, what advice would you give?
So far, the advice has been the other way around, right? The AI guys telling us what to do. And do you have anything to say to the AI people?
Well, actually, this conversation happened again and again in the within Microsoft, right, and even within Microsoft's and his partner like OpenAI. And one of the very typical questions AI researchers ask is, what would the future chip will look like? Actually, they asked the question to NVIDIA guys. So actually, the NVIDIA, so the first reaction is puzzle, because they don't know. They don't know the answer of the future workload would look like. They need that answer to build the next generation chip. So this is a chicken neck problem that would never end seemingly. But as you mentioned, since you mentioned DeepSeek, right? So this is actually a very good starting point. DeepSeek, it's actually the first public known company who co-designed neural network architecture with the underlying chip as well as the network, right? Because as you mentioned, the Deep EP, it is the first known system that advocate to have a perfect computation and communication overlap, right? This is a very good starting point. But if you follow the details, you will see that this is far from perfect, right? Because the detailed hardware overlap will happen in multiple layers. Not only in, so if you take a very grand viewpoint for computation and the communication, this is a very coarse grain, right? Intuitively, it's far from perfect. You need to look at the packet behavior. You have to look at the congestion control behavior, flow control behavior. Otherwise, how do you implement those, the so-called the perfect overlap? So I think this is the good starting point. And for example, for the MOE, right? So networking people as well as system people hate all-to-all traffic, right? I keep asking those machine learning guys whether we can eliminate all-to-all. All reduce is fine, but all-to-all I hate. Can you eliminate it? I think the answer is probably yes, but we're working on that.
All right. Yeah. Okay. So, yeah, one last answer. Yes, you want to say?
Actually, I think whether we should give some advice to the AI person, I think it depends on the use case. So, for example, if you just want to train one large model and you want to co-optimize everything, then you probably need the AI person to understand the underlying network structure. But if we just want to build a cloud and maybe people can, the AI people want to train their model, maybe many different people want to use this cluster to train their model. So in this case, we still want to decouple the AI person and the networking stuff. But maybe the boundary becomes different. For example, maybe the AI person maybe just write some Python code to describe their AI model, and then maybe at for example, at the PyTorch layer, maybe you want to build something, a dependency graph based on the AI code, and then translate to something that is suitable for the network. And or maybe we can also decouple it at a maybe collective communication layer. So the AI model just say I want to use some kind of collective communication. And then it is the collective communication layer that co-optimize the communication and the underlying network and the routing. So with this decoupling, I think we can, the AI people can still write the same code. They don't need to worry about everything. We can make it easy to use. That's my understanding.
Okay, so maybe you can talk offline more. Okay, so
Can I add a quick one? Sorry, Gil, from here.
Okay,
if I understand the question correctly, I think, AI people, they don't want to understand network. What they really want is a cost model, a very fundamental cost model. They want to know, if I do that, how much will it cost me? It's for us to give them a good abstraction with a good cost model so they can ask the question and not go to you, but, type, here is my question and get an answer. This is the cost of doing all-to-all on that network with that size of process group and that size of data. That's all they want. They don't want to understand network. I'm sure they don't want to ask you about congestion control.
Okay, yeah. So I have to conclude the discussion by thank all the panel members and Gil in the audience. And And this is the very end of this year APNet. A very brief ending words. I really appreciate all the effort from PC chairs to come up with such great program, and general chairs leading the organization committee to make everything smooth, and a great banquet last night at the Peace Hotel. And I also want to thank all the audience, stay here, and I hope you learned from this year APNet and continue to join us next year. All right, I thank you all.